Okay, so basically the last part is about learning, okay, and so the idea here is that there are two things actually that you could be interested in learning. The parameters of the network, meaning the probabilities in the conditional probability tables, for instance, or in a sense, if you have more continuous distribution, the parameters of the distributions. For the continuous Bayesian networks, there are a little bit of caveats for doing efficient inference. So if we have time, I'll give you a few hints at the end. But let's by now assume that we are talking about discrete variables. And then the second part is learning the structure of the network, so the edges in the network. Okay, let's start with parameter estimation, and then if there is enough time, I will also describe a bit how to do structure. Otherwise, I will give you hints on how to do that. So in parameter estimation, basically, you assume that the structure of the network is given because you interacted with the domain expert, you had a way to decide which connection should and should not be there, okay? But you don't know about the parameters to attach to the conditional probability distribution of the nodes. What you do have instead is a data set, okay, for the phenomenon you are trying to model, okay? And the data set D is basically a collection of configurations, okay, x1 to x capital N, where here I put parentheses because each configuration is indeed a structured object, which is a configuration for all the variables in the network, if it's a fully observed data set, or some of the variables if you have missing data, okay? So if you think about the previous examples in the sequence, each configuration is a sequence of variables, variable values, okay? And possibly you could have some values which are missing. And now what you need to do is to estimate the parameters of the model, of your graphical model, okay? That best fit your data. Now the simplest approach for learning the parameters is maximizing the likelihood of the data given the parameter themselves, okay? Now, I don't know if you are familiar with maximum likelihood estimation of parameters of distributions. Are you? Yeah, okay. So we'll see that this is really boiling down to maximum likelihood estimation of single distributions, okay? So the idea here is that you want to maximize PD, the probability of the data set given the parameters, okay? And now here is a graphical representation of what's happening. A nice thing with Bayesian networks is that you can use the Bayesian network framework also to graphically represent not only real structure of networks, but also, let's say, situations involving probabilistic reasoning and probabilistic learning. For instance, what happens when you have multiple examples in a data set and you want to understand the connection between these examples, okay? So here, what I have is, I have a very simple network, okay? Tail-to-tail connection, okay? X1 goes to X2 and X3, okay? And now I'm replicating this network once for each configuration in my data set, okay? So this is the network for the first example, okay? So this is the value of X1 in the first example. This is the value of X2 in the second example. In the first example, the value of X3 in the first example, and so on, okay? So you have N, capital N replicates on the network, each with its own values. And now here, these are the parameters of the network, okay? So X1 has no parents, so theta 1 is its parameters, okay? And theta 2, 1 are the parameters of variable 2, because variable 2 depends on variable 1. Theta 3, 1 are the parameters of variable 3, which depends on variable 1 again. Okay, so 3 given 1. Okay, and now what happens is that I'm modeling, okay, the probability of the data given the parameters. Okay, so when I say given, I color, okay, with solid color, what is assumed to be given. Okay, this is also interesting because it points to the fact that when you say given, it doesn't necessarily mean that it's the evidence. Okay, in likelihood, actually the evidence is on the data, but when you compute maximum likelihood, you compute the likelihood of the data given the parameters, and you maximize all the parameters. Okay, so here given means assuming they are given, but not there is evidence. Now, in terms of if I decompose this network, okay, this joint probability, okay, basically I have that each parameter has an arrow to the variable it represents, okay, for all the examples, okay? So theta 1 is connected to x1, x2, x1, 1, x1, 2, x1, n, and so on. Theta 2, 1 is connected to the corresponding variable for all the examples, okay? Now, and at this point, this entire joint probability, if you look at it and you try to read independencies, okay? Now, look at the connection between different examples, okay? Here I have x1, for example, 1, and x1, for example, 2, okay? Here there is a tail-to-tail connection, and I'm assuming that the parameter is given, okay? If the parameter is given, information doesn't flow, okay, from here to here, okay? Same holds here. Given that the parameters are always, right, connected to the variables, okay, in this way, if they are assumed to be given, there is no information flow, okay? So this implies that all the examples are independent of each other given the parameters, okay? And so you can compute the probability of the data set given the parameters as the product of the probability of the examples given the parameters, okay? This is what's called the IID assumption, okay? Independent identically distributed assumption, okay? Now, at this point, you can take this, P of xi, again, I stands for ith example in my data set, and break it down according to the decomposition of the Bayesian network, node given parent. So M is the number of variables in the network, okay, in the single network, and xj is the jth variable, 1, 2, 3, okay? So you have that this probability decouples as the product over j1 to m of p of xj given its parents, paj, for example I. Okay? So this is just decomposing the probability according to the Bayesian network structure. Okay? And now, if you think of it, okay, the probability of variable j given the parent does not depend on all the parameters, but only on the parameters affecting its distribution. So what I called theta xj given the parents. This one, x1, x2, is only affected by theta x2 given 1. Okay? So here you can have disjoint distributions for each condition probability table, okay? Or condition probability distribution in general. Okay, and now this also means that if I want to maximize this function with respect to theta, I can basically focus on each conditional probability distribution separately. Okay? Okay, because theta of 2 given 1 will not be affected by the part of this stuff which involves theta of 3 given 1. Okay? So I can break it down, this maximization, into separate maximizations for each probability table. Okay? And each of them, basically, each table is given by the J. J is the node in the network. Okay? X1, X2, X3. So each theta J given the parents, okay, is obtained maximizing the probability of Xj given the parents, okay, product over all examples in my data set. Okay? So here, if you want, the notation is a little bit heavy. I understand this. But if you follow the intuition, you should also be able to follow the notation, okay? Because the intuition ends up being pretty simple. Okay, so here I removed the product over M because I'm focusing on a single node, Xj, and I'm computing the optimal parameters for it. Okay? Now, as we saw at the beginning, a discrete conditional probability distribution can be seen as a table. Okay? You have configurations for the variable you are considering, Xj, okay, with all its possible values, and you have configurations for the parents of the variable. Okay? Let's say you are the parents. You have and you have a parameter for each possible value of x given a configuration of values for u. So you have a parameter theta for lowercase x, one value of x, given lowercase u, one value for the parents. Let's say the probability for alarm given burglar and not earthquake. Okay? Okay, and now what happens is that this probability, okay, what it ends up being for each possible example, what is the probability of the value in the node x, okay, xj. Okay, here I'm just removing the j because I'm talking about an arbitrary node x. Okay, so that's x1, x2, x3. Okay, but I call it x to remove a bit the complexity of the notation. So x is a node in the network, and I want to compute the parameters associated to the probability of x given its parents, okay, by looking at the product of these probabilities for all examples in the dataset. Okay, so if you think of it, p of xi given the parents of I, what is it? It is the parameter associated to the value of xi given the value of the parents. In the table, you look where the configuration that you read in your example is, and this is the probability. Okay? So for instance, here you have, for example 2, you have the parameter associated to alarm given burglar, not earthquake. Example 3, you have alarm, burglar, and earthquake, so you will put probability of alarm given burglar and earthquake. Okay? So in each example, you will have the parameter associated to the value of x, xi, given the value of the parents, ui. Okay? Product over all examples. Okay? Overall, if you look at it from the viewpoint of parameters, okay, each parameter, x given u, okay, is seen a number of times, which is the number of times in which u and x appear in my dataset. Okay? So, for instance, if I have, let's say, alarm, burglar, and earthquake, and here I have yes, no, no, yes, 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 no, yes, no, no, okay, and so on. Okay, the product, okay, of P of alarm given burglar and earthquake, okay, for all the examples, what is it? It is theta y given nn times theta y given yy, theta y given yy, and so on. Y given yn, theta y given nn. Okay? Overall, you get theta y given nn to be the number of times in which this appears, which is 1, 2, 3, 2. Okay? theta y given y, it appears twice, again 2. Theta y given yn, it appears only once. Okay? So eventually this goes into something like the product for all possible configuration of the parents times the product for all possible values of the variable of the probability associated to variable given parents to the number of times in which you observe that in the examples, in the data set. And ux is the number of times in my data set in which I see x and u, okay, for the value of the variable and the value of the parents. So here you have twice for this, and so on. Okay? And now, if you have this, what happens is that basically, okay, if you do maximum likelihood here, so you try to compute the value of theta, which maximizes this product, okay, with the additional caveat that this stuff should sum to 1, theta xu should sum to 1 if you sum over x. Okay? Now what happens is that this becomes, basically you can break this down into independent computations for each of the columns in your probability table. Okay? Each column is x, possible values of x given configuration of the parents. So one column is A, true or false, given that B is false, E is false. Then another column is A, true or false, given that parents are both true. Okay? When you sum over A, you should get 1. Okay? So these columns are separate probability distributions, okay, which if it's binary, they are Bernoulli. If it's more than 2, they are multinomial. Okay? But they are separate discrete probability distributions. Okay? And now this basically ends up into doing separate, okay, maximum likelihood estimation for each of the columns in the table and then for each of the tables. Okay? So if you go down breaking things, okay, learning parameters in Bayesian network when you have fully observed data ends up being local maximum likelihood estimation for the conditional probability distribution associated to the columns of the tables. Okay? And I will not go into the detail of derivation because, I mean, many already know it, and we don't have so much time, but the maximum likelihood estimation for a multinomial distribution is just the fraction of counts. Okay? So if you want to compute the maximum likelihood estimation of x given u, you take the number of times in which you have ux, and you divide by the sum of these counts over x. Okay? So here, for instance, the probability of y given nn is the number of times in which you serve y and nn divided by the number of times in which you serve y and nn plus not y and nn. So the parents stay fixed and you move the node because the node has to sum to 1. Okay? So it's the normalized counts. Okay? This is binary. For a multinomial, it's the same. Okay? You sum over the possible values. Okay? So basically, the maximum likelihood estimation boils down to separate normalized counts for the tables. Okay? So if you think of it in practice, you have tables, you put the counts for each possible configuration, and you normalize the columns. Very, very, very simple. Okay? Now, there is one problem here, and I already highlighted in this way. In this case, most of the probability here will end up being 0 because many configurations I don't see. Okay? In general, I mean, maybe not most, but there will be configurations with heads which have 0 probability. Okay? Now, this is called, is one of the, let's say, instances symptoms of overfitting your data. Okay? You are giving zero probability to a configuration just because you never saw it in your data. Well, if I have 10 trillion data, maybe that makes sense. But if I have 1,000, okay, or even 100,000, not entirely sure. Okay? So what, I don't know, maybe Fabio talked about this yesterday, but what we do typically in machine learning when we want to avoid overfitting is to do regularization, okay? Regularization means try to add some kind of, try to make the model less complex, okay? Then, and still fit the data. So trade-off between model complexity and data fitting. In Bayesian terms, what we do is we introduce priors. Okay? Priors are probabilities which do not look at data. Okay? So the priors are on the parameters. Okay? Instead of doing maximum likelihood, you do maximum a posteriori. Maybe people already saw it, somebody. But what you do is instead of just maximizing the likelihood, you add the prior probability on the parameters, and you maximize the posterior of the parameters given the data. Actually, so the probability of the parameters given the data, okay, is P of D given theta times P of theta divided by P of D. Okay, so this is the likelihood, probability of the data given the parameters. Okay. If I also introduce a probability on the parameters, a prior probability, and then I'll tell you what it means, I can do Bayes' theorem to get the probability of the parameters given the data, and then maximize this instead of this. So you maximize the posterior instead of the likelihood. Okay? And you incorporate also the prior. Okay? Given that this evidence, PD, doesn't depend on theta, this is constant and you can remove it, and so you get this. Okay? You maximize likelihood times prior. Okay? What is this prior? Well, the simplest possible prior means an informed one is something like uniform, right? Everything has the same probability. Okay? So in terms of discrete distributions, a prior for a discrete distribution is a prior which gives equal probability to each possible configurations. Okay? I don't know how deep to go into this, but when you combine likelihood and prior in probabilities, you would like to have that the formula for the likelihood nicely combines with the formula for the prior, so that when you do this, okay, you don't mess up the mathematics. Okay? So this has to do with conjugacy. Okay? If the distribution for this, the prior, and the distribution for the likelihood are conjugate, okay? So this is the conjugate prior of this. When you do the product, the posterior will have the same distribution, same form of distribution as the prior. Okay? So it will just be something like an updated prior. Okay? I don't know if you are familiar with this stuff, but this is the intuition. Okay? So the conjugate prior for the multinomial distribution is the Dirichlet distribution. Okay? The Dirichlet distribution is a distribution on the parameters. So it's a distribution, if you think of the multinomial as like a die, okay, that you throw, and it's like six-phased. This is a typical, from statistics, multinomial distribution. The die has a probability of ending up in a phase. If it's unfair, they are not equal. Okay? A Dirichlet distribution is like a bag of dice, okay? So that you can pick a die from this bag, okay? And depending on how these dice in the bag look like, it's more likely to pick a fair die, an unfair one, and something like that, okay? So your prior is a bag, okay? And if you think of it, later. And so if I do maximum a posteriori estimation, okay, including the prior, basically what happens is that instead of doing nux over sum over x on nux, okay, you add some components which have to do with your prior, okay? In Dirichlet distribution, basically the prior is something like this, okay? Without going deep into the mathematics, basically what happens is that you can think of a prior as some imaginary samples for the configuration, okay? So a Dirichlet prior, you can look at it as a number of imaginary examples for the first phase of the die, the second, the third, or number of configuration for raining with sun, raining with not sun, not raining with sun, and so on. Okay? This number doesn't have to be integer, it can be fractional, whatever. Okay? But you have imaginary samples. Okay? These imaginary samples are called alpha xu. Okay? And when you normalize, you don't normalize only the true samples that you see in your data, but you normalize the sum of the actual samples and the imaginary samples. Okay? So you augment the counts that you see in your data with these imaginary counts. Okay? And the simplest possible way you can look at it is you assume by prior that any possible configuration appeared at least once. Okay? So this alpha is 1 everywhere. Okay? So, and if you think of it, if you visualize the conditional probability tables, this is like take the table, put 1 everywhere, and then sum the actual counts in your data. Okay? And then normalize. So in practice, let's say, practically speaking, it's very simple adding these priors. Okay? You put imaginary counts in your data, maybe 1 everywhere. Okay? And then you put the evidence and combine. Okay? And the more evidence that you have, the less these initial imaginary counts will be important. Okay? So the more evidence you collect, okay, the more it dominates over the prior. Okay? Because the number of actual counts will dominate over the number of imaginary counts, which is probably 1. Okay? But still, no configuration will be 0 unless you really say in an imaginary count there is nothing there. Okay? And so this saves the problem of the zero probability and also smooths a bit the distribution. So it provides some regularization. Okay? Now, this, practically speaking, is very simple, but there is one caveat, okay? That it only works if you have complete data. Because if you look here, okay, now I could compute the counts on my data, because for each example, I had the value of the variables for all the variables, okay? But suppose that here, I don't know this value, and I don't know this value, and I don't know this value, okay? And this is a pretty common situation, because think of medical domain, okay, in which you build the Bayesian network for diagnosis and so on, which is very common because then physicians like to know what's happening. So they like to have this idea of probabilistic relationships and so on. There, I mean, it's pretty unlikely that somebody took all the possible exams. It's more likely they took none of them, okay? So you have a lot of missing data. And if you have missing data, you can't compute counts. Because what is this contributing to? Why, or why, no? You don't know, because the last one is unseen, okay? And now, you need to account for this. In principle, the full Bayesian approach will tell you that the probability for the new example is obtained by marginalizing out all possible missing values. It becomes completely intractable, okay? But there is a way to deal with it, and it's you don't know the value here, but if you had the Bayesian network already trained, you could infer the value, or rather the probability that this is yes or no, given the other values that you have. Okay? If this is yes and this is yes, this is more likely to be yes or no. Okay? Let's say 70% against 30%. Then this one will contribute 70% to the yes, 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 and 30% to the yes, yes, no. Okay? So in a nutshell, the technique is like this. You have a Bayesian network already trained. You estimate the values here, okay? Not really the values, but the expected count according to the other seen value, okay? So this expected count will be 0.7 in one case, 0.3 in the other, let's say, okay? And you use this to do maximum likelihood estimation, so to normalize counts, but using these expected counts instead of the true counts. The problem is that you don't have the Bayesian network trained because you are actually using these to train the network, okay? And so you go iteratively. You start with a network, maybe trained only on the full observed data or randomly initialized. You use this network to estimate these expected counts, and then you use these to update the parameters. Now you have a new network, and you iterate. You again re-estimate new refined estimates of these probabilities, of these expected counts, and you re-normalize the parameters, and you iterate. Okay? This procedure is called expectation maximization, okay? And it's something which works on expected counts rather than actual counts. Here is how it works, okay? In a nutshell, it's how I said, okay? A little bit more formally, this is how it works, okay? Now, you would like to compute, instead of Nijk, what is it? It's the number of times you observed, okay, for variable I, value k, given that the parents of the variable I have value j. So j is a configuration for the parents, k is the configuration for the variable. So I is the index of the variable, j is the configuration of the parents, k is the configuration for the variable, okay? Now, this Nijk, you can compute if you are fully observed, you can't if you are not. So what you do is you compute the expected value of this according to the probability, okay, given my current data set and theta, which is the current version of the weights, okay? And this works in this way. You sum over all examples, okay? What is the contribution of the health example? Okay, it is the probability that the ith variable, okay, in the health example takes value xk, and the parents of the ith variable in the health examples take value paj, so value j, okay, given xl, which is basically what you know about that example, okay, and the current version of the parameters, okay. Now, if xl has actual values for both xi and its parents, okay, then it's easy because this probability is 1 if the value is xk and paj. It's 0 if the value is something else, okay. So if this specific configuration is observed in your example, then this is an actual count, 1 or 0, okay? When either this is not observed or some of the values here is not observed, then you have to do inference. But we know how to do inference, okay? This is probability of some variables given some other. And you do inference to compute this. Okay? Actually, this is typically not the probability of one single variable, but it's more like the probability of a factor. Okay? The conditional probability table is a factor. But this is also simple. You send messages to the factor instead of to the node. Okay? So it's it's just a plain inference task. Okay? Given the current version of the parameters. So you compute the probability of that configuration for the example, and you use it instead of 0 or 1. Okay? And then you sum up overall examples, and these are these expected counts, okay? Once you have collected these expected counts, this is called the expectation step. Now, you do maximum likelihood. So the maximization step simply is finding out the best configuration of the parameters given this data set with the expected counts instead of the true counts. And this is just, again, the normalized version of the expected counts. The expected counts divided by the expected counts over the values of xi. So, apart from the notation, it's just expected counts normalized column-wise. Okay? Again, this procedure has to be iterated because when I update this theta, these new expected counts will change because they depend on the current version of theta. So you iterate this procedure, okay, until nothing changes anymore. Okay? This EM algorithm is guaranteed to converge to a local optimum of the likelihood function. Okay? There are other techniques, like gradient descent, but I mean, this is, I think, enough. And it's very easy to do the same for maximum a posteriori by just adding the imaginary samples to this whole reasoning. Okay? So nothing really changes, you add this. Okay? These imaginary samples. So it goes like imaginary samples plus expected counts, normalized. Okay? There is one final thing we are left with, which is structured learning. Structured learning is tricky because it's learning a structure, so it's combinatorial. Okay? All possible combinations of edges explodes combinatorially, of course. Okay? And so there are a few approaches there. The simplest, in a sense, is called constraint-based, and it's based on statistical tests. You apply statistical tests to a pair of variables, trying to verify whether they are directly dependently according to the data. Okay? So if you can read a dependency from the data, and if you can, you put a link. Okay? Now, score-based is more complex because what you do is you have a way to assign a score, a probabilistic score, to an entire structure, okay? Which is basically has to do with the probability of the data given the structure times the probability of the structure. In a sense, it has to do with how well the structure fits the data, okay? And then you have, there is a search procedure, okay? You start with a certain structure, like all disconnected or all connected or random, and you start moving in this space guided by the scoring function, by adding, flipping, or removing edges, okay? And you go on trying to increase the score, okay? Until you see that the score doesn't increase anymore for a number of iterations or things like that, okay? One thing we discussed a bit in one of the breaks is that, as I said, in Bayesian networks you have equivalence classes, okay? Different networks which encode the same independencies. This means that when you learn a structure, basically you learn an equivalence class of structures. And there is also a way to efficiently describe an equivalence class of structures, okay? But I will not go into the details. The final, in a sense, fully Bayesian approach would be, no problem, you don't know the structure, you take all possible structures, you compute the probability times the prior on the structure, and you sum up, okay? This is undoable for, all but very, very few variables, but it makes sense to, let's say, maybe average over high quality structures rather than taking a single one, like ensemble methods, okay? When you're interested in doing reasoning, it's easier to have a single structure. But if you're interested in maximizing accuracy or so on, then ensembles can help, okay? I think I could stop here. If you want, I can go a bit into how score-based works, but I don't know, tell me. The overview should be reasonably clear. Tell me if we... You
can spend 10 minutes more, it's okay for you?
Okay, yeah, sure, no problem.
So,
okay.
Sorry, I don't know if
maybe, well, yeah, maybe we should first ask for questions and see if you are convincing enough that you spend time in questions rather than additional stuff.
So apparently there are no questions. So we can go ahead. Thank you.
Okay. So let's see a bit how structured learning works. Okay. Again, if you want, there is a problem because when you learn a structure, you should also both learn the structure and then learn the parameters of the structure and combine the two things together. Okay. Now, let X be the set of variables of interest. Okay. Now, all possible structures that you can build on that are all possible directed acyclic graphs. I don't know if I said it at some point, but the Bayesian network doesn't have to have cycles. I mean directed cycles, not paths, which are cyclic, but if you follow the arrow, you go in a cycle. This is not possible. Okay. Anything which doesn't have a cycle is a candidate. Okay. And now you have the data set of observations. Okay. Now, let me skip this, which is the really fully Bayesian approach. And let's say that if you want to find out a high-quality structure, what you can do is you can try to maximize, again, the likelihood of the data, not given the parameters, but given the structure, over structures. Okay? Or you can maximize the likelihood of the data times the prior on the structure, and so have a maximum a posteriori estimation. Okay? For instance, again, this is, it's even clearer that this has to do with model complexity and so overfitting, because in the prior on the structure, I can say that a structure with less edges is a priori more probable because it's simpler. Okay? So if I have to prefer to trade off, to choose between two structures which are roughly the same in likelihood, but one has very less edges, this second one would be better because of regularization and model complexity considerations. Okay? Now, how to do a maximum likelihood, okay? First of all, well, you have to see how to estimate, okay, the likelihood of the data set given the structure, okay? Because the likelihood of the data given the parameters, we know, okay? You take the composition according to the structure, you put the conditional probability distributions, and you get the joint. But what about the structure? Because you miss the parameters, okay? And now, one possibility would be to do a maximum likelihood approximation over the parameters given the structure. So compute PD given S, the maximum likelihood, the likelihood of the data set given the structure, as the maximum over the likelihood given all possible parameters. Okay? Now, the problem is that this, again, has to do with finite sample and complexity. What ends up happening is that in this case, you will have higher probability by putting edges between pairs of variables, provided there is some mutual information between these two variables. But if you have a finite sample, having zero mutual information between two variables, any two variables, is almost impossible. Okay? Just because the sample is finite, okay? If you take a Bayesian network, okay, with some independencies, and then you sample, okay, 10,000 examples from this Bayesian network, and then you try to see whether these samples satisfy the independencies, they will not perfectly satisfy the independencies. Because of the finite sample, there will be, by chance, some kind of minimal dependency, okay, coming out. Okay? So if you do vice versa, you will end up putting links everywhere and having a fully connected network. Now, what you do is something different. This is called Bayesian Dirichlet scoring. Okay? And this is the reasoning. We start with a simple case with one variable, and then we generalize. Okay. Now, let's say we have variable with a multinomial, so R possible realizations, like an R-phase die. Okay. And then the variable, the structure is a single node. Okay. Now, the probability distribution associated to this network is a multinomial distribution over the variable and Dirichlet priors over the parameters. Okay. With values alpha 1 to alpha r. These are the imaginary samples. Okay? Now, your data set is a sequence of n examples, which are realizations of the die. Okay? And now, let's take our data set, and let's sort it according to the value that comes out. It's irrelevant how you sort it. The result is the same. Okay? So D, because the examples are IID, okay? So D is x1, x1, x1 for the number of times in which you have x1 as a result, x2, 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 and so on. And now, this probability, the probability of D, written this way, given the structure, okay? Here I simplified this notation, writing P subscript structure of D. Okay, it means P of D given the structure, so that then you have you don't bring this given S everywhere. It's implicit in this subscript. Okay. Now you can break this probability down. Okay, into by the product rule, okay, into the probability of, watch out that here you can't say, okay, everything is IID, because you don't have the parameters yet, okay? Everything is IID given the model, which is a structure and parameters. But you can apply the chain rule, which says that the joint is decomposable as one variable given the others, and repeat, as we were doing in the topology-oriented kind of version, right? So you take a product over all possible examples of the probability of one example given the previous ones, okay, given the previous data set. So you get P of x1, P of x1 given x1, P of x1 given twice x1, and so on. Then you have P of x2 given all the previous x1s, and so on. Okay? And now, what happens, okay, and here you have to, in a sense, trust me about Bayesian parameter estimation, which ends up producing the same result as maximum a posteriori, but it's reasonably intuitive. The probability, okay, that one example, okay, takes value xk given the previous examples, okay, is basically the fraction of times in which you see that type of example given the data set. Okay? So the current counts for that value. Okay? Okay? So if you see it statically speaking, the probability of a certain value, what is it? It's the fraction of times you observe that value in the data set. Here is just the fraction of times in which you observe that value in the previous data set up to that point. Okay? Plus the imaginary samples. Okay? So nkt is the number of times in which you observe xk in the first t examples. And you use this to estimate the probability that t plus 1 is xk. And then you keep aggregating. At this point, you can multiply all these probabilities. Okay? Each probability depends on the previous observations only. Okay? And so the result, and here I'm sorry, mathematics get a little bit complex, but it's better to get the intuition. Here you basically end up having something like this. This is rather simple because it is the first case, okay, x1, you never observed it, so it is a1, samples, imaginary samples for 1, divided by a. A is the sum of the imaginary samples, okay, for all possible values, okay? So the first x1 has a probability a1 divided by a. The second x1, now you observed it once, so the second x1 has probability a1 plus 1 divided by a plus 1. And so on for all the x1s that you observe. So the n1 is the number of x1s that you have. So when you go, the n1 x1 has a probability which is a1 plus n1 minus 1, the previous ones that you observed, normalized. Okay? And then you move to x2, and in x2, you never observed it before, so you have alpha 2 divided by what you have up to now, alpha plus n1, the examples that you saw up to now, and you go on for x2. And then you go to x3, and you go on for the others. And you keep accumulating probabilities. Okay? And this is the score of the network for one single node. Okay? I will not go into the detail of this because it's a way to write this compactly using gamma functions. If some of you is familiar with gamma functions, then it's reasonable, easy to see. But if you are not, if you look at the slides, you can see that by using this definition of the gamma function, you will see that you can compactly write all that stuff like this. But it's not very relevant for our discussion. What is relevant is that there is a way to progressively compute this probability rather than there is a way to compactly write it down. Okay? And then, in the general case, you just do the same thing for all possible nodes, for all possible parents. Okay? For all possible nodes and all possible parents, you have a configuration for the node given the parents. Okay? And ijk. Okay? So you generalize from one node to the network. And this gives you the score of the network. It's called Bayesian-Dirichlet scoring. Okay? And now once you have this, and the nice thing of this score is that it's decomposable. Okay? It is the product of independent scores associated to each node. And this is very nice because then you need to do search. Okay? So when you search, if you change a node, you don't have to recompute the entire score from scratch, but only what's affected. Okay? And now what you do is you start searching. Okay? And there you can use all possible heuristics for local search and so on, given that you have a scoring function and an efficient way to update the score because of this decomposability. Okay? Actually, there are also people casting it into MILP, into integer linear programming, okay? Combining constraints with the scoring, the decomposition, and doing ILP solving for that, okay? But this is kind of the idea behind, let's say, strong approaches to structured learning, okay? And I think this ends up.
So I have a question, since I'm very interested in this sort of topic. And which one is the approach that you would recommend, which is both, which would provide good results, and at the same time is has a low complexity? So which is the approach that you would recommend?
Well, what I see, I'm not really, let's say, an expert in state-of-the-art on structured learning for Bayesian networks, but I know a bit, and I think that the most promising approaches at the moment are the ones casting this in terms of integer linear programming. So trying to do solving with ILP solvers. Sorry?
With the score?
With this score, yes, because this score is decomposable, and so it helps to break it down and do linear programming. So yes, that's what I would say. And it's also interesting because then you can also add constraints, okay, on the structure of the network.
So the constraint will be constraint on the structure.
On the structure. Yeah.
You already know in advance either how you would like the structure to be, or maybe you have some pre-existing knowledge on the structure.
Yeah. Yep.
I have a question. So, at the state of the art, which are the open research problems in, in developing like methods and algorithms to do inference on graphical models?
Hey, well, there is a lot. There is a lot. Probably the most efficient approaches are the ones based on variational inference, in which you try to approximate the distribution with simpler models, parametric, which for which then inference is exact, but then you have an approximation. Okay, but all this has to do with finding the right variational model, and it's not. One thing that I would say is that now there is a trend in trying to build up, let's say, frameworks which, in a sense, compile your problem so that efficient inference algorithms can be run on your model by adapting existing algorithms to your task. So things like Edward, for instance, is a library which does efficient approximate inference using things like variational, but also Markov chain, sampling methods. And it allows you to write down the definition of your network with things like TensorFlow, and then exploit, compile the network and do efficient inference. So I would say that one of the avenues at the moment is trying to hide, right, the complexity of the inference by doing, let's say, smart optimization, as people do in neural networks, right, in which they basically the smart optimization of the parameters is left behind to the computation graph and how to craft it for GPUs or for TPUs and whatever you have, and you just describe stuff at the high level. I think this is especially in terms of applicability, and this is because, again, the more complex you go with the models that you want to describe, the less easy it is to do efficient inference. Okay, and then you have to go for smart techniques, and it's not for everybody. And so being able to decouple these two things is something which I think makes these techniques much, much more appealing.
So I have a question, which is about the IID assumption. So I'm wondering then, what's going to be when the data is no longer IID distributed across samples? I mean, this is opening up, I imagine, a big...
Yeah, well, it is, because we don't even know, in a sense, how to do a proper evaluation of performance in this case. Because the proper evaluation of performance, you do accuracy estimation by sample accuracy on your data set. But if your data set is not IID, I mean, you can't do sample accuracy because, I mean, samples are correlated, okay? And so, in principle, one should take, let's say, everything which is dependent of each other and see it as a single example. In a Bayesian network, it's not that difficult, okay? Because in general, you can take examples and see them as a single large network, as I was showing before. And then the decomposition only happens when the examples are really independent of each other. But the framework still holds, okay? It is more a problem for, let's say, techniques which are more crafted for looking at independent samples, like kernel machines or neural networks, which But in that cases, neural networks, especially, people don't care incredibly much about consistency. So, but in kernel machines, for instance, you have, for instance, techniques like, I don't know, kernels on graphs, in which the graph is not your object, but your object is a node in the graph, and then you do these diffusion kernels in order to propagate information along the graph, okay, and do similarity in terms of shared paths, distances, and so on. But in general, I would say that the proper way to deal with the non-IID data is not to consider them IID, and so to deal with them jointly. This has to do also with statistical relational learning, is doing things like that. So
is this a field of interest? So there is work going on in that direction? There's a lot of work.
There is work, again, I would say that all the work about statistical relational learning, which tries to combine statistics view on models with relational data, typically has this problem, because if you go with relational data, the probability that you don't have independent examples grows. And in many cases, you have just one big example, which is your data set, which is fully connected. And so, but I mean, there are a lot of unsolved problems also there.
Thank you.
Thank you, Andrea.
Okay.